Hello, am I audible? Hello.
Yes, madam.
Oh,
Yes.
and my screen is also visible, right?
Yes, ma'am.
Okay. So we'll just wait for a few minutes and then start.
Ma'am,
Mm, yes, yes.
hello.
Hello, yes.
Ma'am, is there any particular books or graph theory that can I?
Oh, yes. In the course structure, there are three books mentioned, right? There's this book by West on graph theory. In
Yeah.
Yeah, so there are three books mentioned. You can refer to those. Have you looked at those?
No, ma'am. If you give reference, then I will prefer.
Okay, so I'll just I'll write. Okay. Okay, so if you were asking for references, so these are the three, like are these name visible? So
Yes, ma'am.
these are the three books that are mentioned in the course structure only. Like if you'll go to the NPTEL graph theory page, so these you can look at these books.
Okay, okay.
Okay. Okay. So now,
Thank you.
yeah, yes. So now I'll begin. Okay, so good afternoon, everyone. I welcome you all to the sixth problem solving session of NPTEL Cross Graph Theory. So today we'll be discussing about connectivity, and in the end we'll also discuss about networks. So first, let's recall some concepts on connectivity that was covered in the course. So first thing is of the vertex cut. So what is so for today's session we are looking at connectivity in the sense that how connected are the graphs. So like if we can measure the connect, so we'll be mostly concerned with connected graphs. So now if G is a connected graph, what do we mean by a vertex cut? Vertex cut is a set of vertices in V such that if we remove those vertices, the resultant graph become disconnected. So these are some examples of graph G1, G2 and G3. So a vertex, so if we remove this vertex C, the resultant graph is like this, AB and DE. So if we are removing a vertex, and we can see that this graph is disconnected. So if we remove that vertex, and if we look at the remaining graph, this is becoming disconnected. Therefore the vertex set containing just the vertex C is a vertex cut for this graph. And similarly, if you look at G2 or any bipartite graph, you can see if you remove any one of the partition, like if this is partition A or partition B, if you remove any one of these partition, since there are no edges within the partition, so if you remove A, the and provided all the and provided those partitions have more than one vertex, if you remove A, then you'll see that you're left with just two vertices. So if A and B in this graph in G2, A, B form a vertex cut. And similarly, if you look at this G3, and if I name these vertices A, B, C, D, E, F, G. So if I remove A and G, my resultant graph will look like this. Okay. So if I remove A, G, the resultant graph will be, we have this B, C, then we have D, E, F. We have this D, E, and F. We see that after removing A and G, the graph is becoming disconnected. So A and G are also forming the vertex cut. So in G3, can you give me any other vertex cut? Basically set of two vertices which is making this graph disconnected other than A and G.
Ma'am, DC.
DC, yes. If we remove D and C, then also we see that graph is becoming disconnected. A and B will be in one component and G, E, F will be in other component. So there is no, if we remove D and C, there is no path between B and G. So we see that this graph is becoming disconnected. Any other example of vertex cut in the same graph? So for G3, for G3 we have got two examples. If we take S1 equal to CD, then also it is becoming disconnected. If we take S2 equal to AG, then also this graph is becoming disconnected. Any other example? Any other vertex set?
Ma'am, EG?
So you're saying E and G.
Yes.
So I'll mark those vertices. You are saying this and this, right?
Yeah.
So if you'll remove E and G, yes, then also graph will become disconnected because we will have F in one component and all the other vertices in no, good. So E and G is also a vertex cut. Yes.
Ma'am, vertex cut is the minimum, or we can say A, D, and E is also a vertex cut.
Yes. So what? No. When I'm just saying vertex cut, it means any set of vertices which after which removing it, we are getting a disconnected graph. So it need not be minimum.
So can
When
we,
we'll
so can we,
specify, yeah, yeah,
so can we remove A, D, and E?
A, D, and E. You're saying A, D, and E, right? So, your example is A, D, and E, right?
And G also, ma'am.
Huh. So if you just remove A, D, E, then you see that remaining graph is not becoming disconnected. So A, D, E.
And G also, G.
Huh. So A, D, E is not a vertex cut, but if you remove G also, then it becomes a vertex cut. Yeah. So everyone, I think everyone now understood the definition of vertex cut. So
So,
now,
ma'am, so
yeah.
minimum is not a criteria then?
So when we are just saying that, when we are saying vertex cut, when we are saying vertex cut, we are referring to any set of vertices which are disconnect, which after removal, which is disconnect. But when we say we are looking for a minimum vertex cut, we generally like when we'll be looking at connectivity, then we like I'll be defining connectivity, which will be denoted by kappa g. It will be the size of minimum vertex cut. Okay. So when we are just saying vertex cut, it need not be minimum. But when we are looking at connectivity, then we are interested at minimum vertex cut. Is it okay?
Yes, ma'am.
Okay. So now one if we have understood vertex cut, if we have understood vertex cut, the next topic is k connectedness. So k connectedness means that, first of all, if we are referring to k connectedness, g should have at least k plus 1 vertices, and then we say that g is k connected if and only if we remove less than k minus 1 vertices, then graph should remain connected. Or equivalently, we can say that G does not have a vertex cut of less than equal to k minus 1 vertices. So if you are saying k connected, that G is k connected, then if you are removing less than k vertices, the graph should, and if you are remove any less than any vertices, any set of vertices which are less than k, then graph should remain connected. So this is what is k connectedness. So in this graph, in the first graph, so if we look at just G1, can we say that G1 is 1 connected?
Yes.
So by the definition, 1 connected refers to just, so also 1 connected if n is great, 1 connected refers to just the connected graph with 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 at least 2 vertices. So all these graphs G1, G2, G3 are connected. Therefore, they are 1 connected. But is G1 2 connected? Is G1 2 connected? Is G1 2 connected?
No, ma'am.
No, ma'am, no.
No. Because if we remove one vertex, the graph is becoming disconnected. So it is not 2 connected. What about G2? Is G2 2 connected?
Yes.
Why? Why is G2 2 connected?
Ma'am, if we remove one node from each side, still it is connected graph.
So, so if we are saying G2 is 2 connected, we mean that if we remove, like there is no cut vertex. That is, if we remove any one vertex, then the graph remains connected. So in this graph G2, you can see that if you remove any one vertex, this graph is remaining connected. Therefore, therefore this G2 is 2 connected. But is G2 3 connected?
Yes, ma'am. It is also three connected.
Does
So no,
everyone?
if we remove only orange one, then it is two connected. Now, if we remove three vertices, two orange and one blue, then it is not, ma'am.
So see, there's this confusion. So G2 is 1 connected. G2 is 2 connected because if we want to say it is 2 connected, that means if we remove 2 minus 1 vertices, that is, if we remove any one vertex, then the graph should remain connected. And in G2 we can see, if we are removing one vertex, this graph, if we remove any one vertex, then this graph is remaining connected. Therefore G2 is 2 connected. But if we want to say that G2 is 2 connected, if G2 is 3 connected, then we have to say that if we remove any two vertices, like if we pick any two vertices and remove them, then the graph should remain connected. So is G2 3 connected?
No,
So question is G2 3 connected?
no, madam, no.
Why?
Because if I connect, if I remove two orange
Hmm.
nodes, then it is not connected.
Yes, if we remove two orange nodes, then we are getting three components, three blue vertices, which, so the graph is becoming disconnected. So G2 has a vertex set. G2 has a vertex cut set of two size 2. Therefore, G2 is not 2 connected. G2 is not 3 connected. So now if you see, so this is what k connected means. So k connected is basically if you remove k minus any k minus 1 vertices, then graph should remain connected. Now if this is k connectedness, now what is vertex connectivity? Vertex connectivity is largest k such that G is k connected, or equivalently it is the minimum size of vertex cut or minimum size of vertex cut, or the n minus 1. So if G has n vertices, then it is the largest k which is less than equal to n minus 1 such that G is k connected. So this is what is vertex connectivity. So for G1, what do you think is vertex connectivity?
One man, one.
1, because because for G1 we see that vertex connectivity is 1, vertex connectivity is 1 because G1 is 1 connected, but G1 is not 2 connected. Therefore 1 is the largest case such that 1 is the largest case such that G is k connected. What about G2? What about G2? What is the vertex connectivity of G2?
Two connected.
Sorry? 2. You said 2,
Two
right?
connected.
2
Yes, ma'am.
connected. Yes. So we see G2 is 1 connected, G2 is 2 connected, but G2 is not 3 connected, because if we remove 2 vertices, then this graph is becoming, if we remove 2 orange vertices, this graph is becoming disconnected. So largest k for which G2 is k connected is 2. Therefore vertex connectivity of G2 is 2. So now by the definition only you can see that if G is a graph on n minus 1 vertices, then vertex connectivity has to be less than equal to n minus 1. Or in a, so because what is the definition of vertex connectivity? It is the largest k which is less than equal to n minus 1 such that G is k connected. Now we have this concept of vertex cut. Vertex cut was we just discussed it. It is the subset of vertices after whose removal graph is becoming disconnected. Now similarly we can also define a edge cut. Edge cut will now be a subset of edges such that if we remove those edges, then the resultant graph is becoming disconnected. And we can see that if that edge cut is minimal in the sense minimal in the sense ki, that if we are taking some set, so edge cut, it can be minimal edge cut can be of form this S bar, where S is a subset of V. S bar is V minus S, and this notation bracket S bar refers to a cut where it refers to all the edges. It is contained in subset of edges such that whose one vertex is in S and other vertex is in S bar. So this is, so edge cut is like form, is of form this. So in this graph you see, if we remove the edge, CD, what will be the resultant graph? Resultant graph will be this D E A B C. So so this graph is becoming disconnected. Therefore we see that CD is an edge cut, and in this you can take S to be D. So if you take S to be D and S bar is A B C E, then all the edges from S to S bar is just one edge, D to C. So we see that this is an edge cut. And in this second also we can see that if we remove all the edges which is adjacent to just one vertex, then since this orange vertex has these three edges, and if we remove all these three edges, then this, in the new graph, this orange vertex will become isolated. There,
Madam, madam, sorry.
yes.
Uh, we have to say S is CD and S dash is AB, BC, and CE.
No, I'm just saying S is D, S
D,
bar
D,
is A, B, C, E.
no, ma'am, D is vertex, na? So we have to write edge.
So now, so this is SS bar. Now your this is S and this is S bar. Now your edge cut is basically SS bar, which is all the edges from S to S bar. So it will be just DC. So okay. So
Yes, yes, yes.
yeah. And in this you can see if I name my vertex dim as 1, 2, 3, 4, 5. So in this I can take my S to be 4, 5. Sorry, 4. In this I can take my S to be 4 and S bar to be 1, 2, 3. Then my edge cut is basically 4, 1, 4, 2 and 4, 3. So if I remove these three blue edges, this in the new graph this 4 is becoming isolated. Therefore this is also an edge cut. And similarly you see if I remove this edge and this edge here, so this is also becoming disconnected. This graph has two components. Therefore this is also an edge cut. So does everyone understand the definition of vertex cut and edge cut, or is there any confusion? Okay. So now if we understand what is vertex cut and edge cut, so now we had this vertex connectivity. Similarly, we also have edge connectivity. So vertex connectivity was the minimum size of vertex cut and edge connectivity is minimum size of edge cut. And then we in the lectures course material we have this theorem that vertex connectivity is less than equal to edge connectivity, which is less than equal to the minimum degree. So this is proved in class that so we can see that if we know two of so basically if we want to compute any of these we can use these inequality. So now this was about connectivity. Now let's try some questions regarding this. So now let's first find out vertex connectivity, which is kg, and edge connectivity k dash g for these simple graphs. So first graph is kn. So let's suppose it is K3 first. So what do you think is vertex connectivity for K3? So first of all, it should be less than equal to 2. So it has 3 vertices. It is the minimum size of vertex cut and 2. So for K3, what is the vertex connectivity?
One, ma'am, kg is one, ma'am.
So if you are saying kg is 1, then you are saying that k3 is 1 connected,
Yes.
but k3 is
I
not 2.
think two connected.
But k3 is, what about, is k3 2 connected? Is k3 2 connected?
Ma'am, if we give ABC as a name, so if I disconnect A,
Hmm.
then B and C so still connected, but that A is disconnected. So that is why it is one.
No, no. So when we are removing vertex now, if you are removing vertex A, then A is not in the new graph, right? You are looking at K3 minus A. So then it will be just two vertices B, C, and this is connected, right? So when you are looking at vertex connectivity, you are removing the vertices.
Okay.
So is K3 2 connected?
Yes, ma'am.
Yes. So we see that, and uh, it should be less than equal to n minus 2. Therefore we see that vertex connectivity of k3 is 2. So what about kn now? Or let's first try for k4. So this is k4. Is k4 1 connected? Is k4 1 connected?
Yes, ma'am.
Yes, because 1 connected is just the connected graph, and we see that K4 is connected, therefore it is 1 connected. So what about K4? Is K4 2 connected? Is K4 3 connected? So if K4 is 2 connected, that means if we remove one vertex, then the graph is remaining connected.
Yes, ma'am. Two connected.
So it is 2 connected because it is a complete graph. If we remove just one vertex, all the other vertex, so we are getting, if we remove one vertex, then the new graph that we are getting is K3. So K4 minus V is K3, which is connected. So we see K4 minus any one vertex is K3, which is connected. Therefore, if we are removing just one vertex, then this graph is remaining connected. What about 3? Is K4 3 connected?
Yes, ma'am.
Why? Why is K4 3 connected?
If you remove two vertices, then still the graph is connected, ma'am.
Yes, if we remove two vertices, then we are left with K2. So it is 2 connected. So, and we know that kappa connectivity should be less than equal to 3, and it is 3 connected. So vertex connectivity of K4 is 3. So now can you generalize what is the vertex connectivity of Kn?
N, ma'am.
So
N minus 1.
n
N
minus 1,
minus one.
a
Yes.
n minus 1, because we are looking at complete graph. We are looking at complete graph. So if we are removing Kn minus V1 Vk, then we are left with n minus k vertices. We are left with Kn minus k, and since it is a complete graph, there are all the remaining vertices are connected to each other. So Kn minus, so Kn minus V1 Vk is just isomorphic to Kn minus k, which is connected. And we have that connectivity should be less than equal to n minus 1. Therefore, we have that vertex connectivity of Kn is n minus 1. What about edge connectivity? So now we can maybe use this inequality that vertex connectivity is less than equal to edge connectivity is less than equal to minimum degree. So using this, can we have the edge connectivity of Kn also? So if G is equal to Kn, we have seen that vertex connectivity is n minus 1. What is the minimum degree of Kn?
Still N minus one, ma'am.
It's also n minus 1. So then what will be the edge connectivity?
N minus one.
Yes. So we see that. Therefore, edge connectivity is n minus 1. So in for complete graph, you see we have basically all these three things are coming out to be same. Which is just n minus 1. Now second example is complete bipartite graph where m is less than equal to n. So let's try this also with some example. So if we take K23, then this was the G2 in our original discussion. This was this was this was this was K23, right? And for this we already saw that vertex connectivity. What was vertex connectivity coming out to be for K23?
3 connected.
No, is K23 connected?
Two connected.
It K23 is not 3 connected, because if we remove these two vertices, then the graph is becoming disconnected. So the vertex connectivity of K23 is 2, right? Because K23 is 2, because it is 2 connected but not 3 connected. What about K45? So we have these 4 vertices and we have 5 vertices here, and we have all the possible edges. So what do you think?
Four.
4 connected.
4
Four.
connected. Yes. Okay, so there will be many more edges. So why it is 4 connected? Sorry, why the connectivity is 4?
Because we have four side. One side is four nodes, and another side is five nodes.
and
So
and this is also a complete graph,
yes.
in the
So
complete bipartite. So
minimum of 4 and 5 is 4. So that is why 4 is the connectivity.
yes. Okay. But so this is a bipartite, complete bipartite graph. So so if we so if we see that if we are removing, so there will be all, if I am drawn all, I don't, so yes, 1 2 3 4, 1 2. So see, so we are claiming that K M, the vertex connectivity of KMN is M, if M is less than equal to N. So if we are removing, so now we have to say that it is, to say that vertex connectivity is N, we have to say that it is M connected, but it is not m plus 1 connected. So let's try to prove both of these claims. So first of all, easy one is B. So why do you think it is m, it is not m plus 1 connected?
Because for m plus 1 we have to remove m. So if
Yes,
you remove m, then it is not one side is gone.
one, yes. So basically, if this kmn, it is coming from, kmn is coming from two partition A and B, and order of A is m. So if we remove A, if we look at KMN minus A, we are just left with B. And since this is a graph, all these vertices, they have no edges between them. And therefore, after removing this graph is becoming disconnected. So we see that it cannot be M plus 1 connected. But why it is M connected? So we have, so to claim that vertex connectivity is M, we have to say that this is the largest K for which it is the largest K for which it is K connected. So we have already seen that it is not M plus 1 connected. So we, from this we get that vertex connectivity is strictly less than M plus 1. Now why it is M connected?
So ma'am, remove m minus 1 vertices from one side. So one will be left here.
Yes, one will be left there, so the graph will be connected. But
Yes.
what if we remove some vertices from A and some vertices from B?
But we have to give a case now wherein it will prove that.
No, no, to prove that it is M connected, you have to say that if you remove any set of M minus 1 vertices, then the graph should remain connected. To say it is M connected, if you are removing any M minus 1 vertices, then the graph should be connected.
So, ma'am, for any, I have a choice. I will remove from M set then.
No, no, for any, as in I mean, you have to check for every M minus. So for every set of M minus 1 vertices, if you are, then G minus S should remain connected.
So then,
So if you are, so this is correct. So if you are removing, so suppose in this case only, if we were at K2 3 only, or like if we are at K4 5, so if we are removing three vertices, suppose if we are removing three vertices from A, if we are removing all the three vertices from A, then the graph is connected, because this fourth vertex is then the graph is like this. It is basically K15. So if we are removing three vertices from A, then we are getting a connected graph. Similarly, if you will remove any three vertices from B, then also, so if you are removing K4 5 minus, say these are V1, V2, V3, V4, and this is W1, W2, W3, W4, W5. So if I am removing three vertices from A, then the resultant graph K45, if I am removing three vertices, what is this graph? This is K15, which is connected. Now what if I remove three vertices from W? Then what is my resultant graph? As in, if I remove three vertices from partition B, so what is this graph isomorphic to? If I remove these some three vertices, basically, if I am removing W1, W2, W3, what is the resultant graph?
K12, ma'am.
Uh,
4 2 4 2.
K42, right? K42, which is also
Connect.
connected. What if I remove, now it is simple, right? Now what if I remove one vertex from, if I remove one vertex from first partition and two vertices from other partition, then what is my graph? So
K3 K32 T2.
K32, which is also connected. And the last case remaining is basically if I remove two vertex from partition 2 and two from the first partition and one from the one, then what is my graph? This is just
K24.
K24,
24.
which is also connected. So we have shown that, so this is just one case for K45. So we have shown that K45 is 4 connected. K45 is 4 connected. And we already know that K45 is not 5 connected, because if I remove V1, V2, V3, V4, then this graph is becoming disconnected. So now does everyone understand why vertex connectivity of KMN is M when M is less than equal to N? To say that vertex connectivity is M, we have to say that it is the largest K for which it is K connected. That is, it should be M connected and it should not be M plus 1 connected. So is it clear to everyone?
Yes.
Okay. So now we have find out the vertex connectivity. What about the edge connectivity? So can we so so can we again use that inequality? So KMN, vertex connectivity is less than equal to edge connectivity is less than equal to minimum degree. So vertex connectivity is coming out to be M. What is the minimum degree of KMN?
M, ma'am.
M.
Yes.
Because all the vertices, so if we have KMN, this has M vertices, this has N vertices. So any vertex here will have degree n, and any vertex here will have degree m, and we have already know that m is less than equal to n. Therefore vertex degree, minimum vertex degree is m. And now using this inequality we can say that edge connectivity is also m, right? Okay, so we get that in this case also we are getting that vertex connectivity is equal to edge connectivity, which is equal to the minimum degree. Now last example in this scenario is Cn. Cn is a cycle. So now what do you think about Cn? So if we have a cycle on n vertices, that is n is greater than equal to 3. So what is the vertex connectivity? So first of all, is Cn1 connected? Is Cn1 connected?
Yes.
Yes, because it is a connected graph. Is Cn2 connected? Is
No, ma'am.
Cn2? No. Why? So if you are saying no, then you have to give me a vertex cut of size 1.
No, ma'am. Still two connected.
It is 2 connected because since it
Yes.
is a cycle, if you just if you remove one vertex, you have the other end, right? So is Cn2 connected? Yes, because if we
Yes.
remove one vertex, suppose I am removing this, then all the other vertices, so we are getting a path, so which is a connected. What about 3 connected? Is Cn3 connected?
No, ma'am.
No. Then you have to give me a vertex cut of size 2. So suppose this is my C5. Okay, so this is whatever, like C1. Oh, sorry. This is 1 6 C6. So what is the vertex cut here?
V1, V3, ma'am.
So if we remove
If you
V1,
remove V1, V3.
yes. If we remove V1 and V3, then we see that V2 is becoming isolated. As in the resultant graph will be, so we have one here and other here. So we see that Cn is not 3 connected. So what is the vertex connectivity then?
2.
Vertex connectivity of Cn is 2. What about the edge connectivity?
2.
2, ma'am.
Oh, 2. Okay, 2. Why it is 2?
If we cut,
Minimum degree 2, ma'am.
Yes. So we can either use the same thing, which is kcn is less than equal to k dash cn is less than equal to minimum degree. So this is also 2. This is also 2. So this becomes 2. Now in Cn, can you give me an edge cut of size 2? Basically, if in Cn, can you, so since it is, sorry, edge cut, yes. So edge connectivity is the minimum size of edge cut. That means if we remove 2 edges, then this graph is becoming disconnected. So what are the 2 edges which is making this graph disconnected?
you can cut any two parallel, man. Any
Any
two.
2 disjoint lines, basically. If we are removing any two, like if we are removing any 2 adjacent line, then this won't work. So if we are removing, basically, suppose this line and this line, then the resultant graph is V2, V3. Now if you are removing edges, then you don't have to remove the vertices. Okay. So we see after removing this V5, V4, this graph is becoming disconnected. So edge cut is also 2. Okay. So this was the first example. Now also for complete graph. So it was K4, right? For complete for K4 also, For K4 also, edge connectivity was coming out to be 3. So that means it has an edge cut of size 3. So what is the edge cut here? So that is basically give me 3 edges whose removal is making this graph disconnected. So, so for we already see that edge connectivity for Kn was coming out to be n minus 1. For in particular for K4 it was coming out to be 3. That means if we remove 3 edges, then this graph is becoming disconnected. So what are the 3 edges which is making this graph disconnected? Hint, basically we know that this, how do we prove this thing, that edge connectivity is less than equal to minimum degree. So this is the hint to find the edge cut for this.
So any vertex which is connected, we can disconnect three edges going outside.
Yes, good. So basically how do we get that this edge connectivity is less than equal to minimum degree? Suppose is the vertex v is the vertex of minimum degree equal to k. So if we remove all the edges which are adjacent to V, then in the new graph V is becoming isolated. That means that in the new graph we are getting a disconnected graph. Therefore we see that size of edge connectivity is always less than equal to minimum degree. So now here it is minimum degree is 3. So if I pick any vertex and I remove all the edges which are adjacent to that vertex, so I remove these three. If I remove these three edges, then my resultant graph is this, which is disconnected. Therefore this is the edge cut. And what about KMN? So in KMN, can you give me an edge cut now? So for KMN also, for KMN, edge connectivity was coming out to be M. So or basic, so in particular if you are looking at K32 or K33, this is V1, V2, V3, W1, W2, W3. So we have already computed that edge connectivity of K33 is 3. That means it should have an edge cut of 3 vertices, edge cut of 3 edges. So what are the 3 edges which is making this whose removal will make make this graph disconnected?
You can take any vertex going outside three edges. You can cut that. It will
Yes.
isolate that vertex.
Yes. So basically, if I take this vertex and I remove all these 3 edges which are adjacent to it, then in the new graph, V1 will be alone and we have this V2, V3. So we see that the graph is becoming disconnected because in this new graph, V1 is becoming isolated. So this is the edge cut. Okay. So for these three examples, is there any confusion? Like for this, everything was coming out to be n minus 1. For this, it is coming out to be m. And for this, it is coming out to be 2. So any confusion in these three examples? Okay. Yeah. Now let's let's talk about in particular two connected graphs. So we have, okay, wait. Okay, there were more questions. Okay, so okay, first of all, there are More questions. Yeah. So now next question is, before we go to two connected. So if G is a connected graph on n vertices, then the claim is that vertex connectivity of G is n minus 1 if and only if G is a complete graph. So we proved one condition. We proved the converse, that if G is equal to Kn, then vertex connectivity is coming out to be n minus 1. But this question is saying that converse is also true. That is, if G is a connected graph on n vertices and vertex connectivity is n minus 1, then G is equal to Kn. Or in other words, we have to prove this, that G is a graph on n vertices. G is a graph on n vertices. Then vertex connectivity has to be strictly less than by, if G is a graph on n vertices and if G is not equal to Kn, then vertex connectivity is strictly less than n minus 1. So why do you think this is true? So we have to show this. Question is this, that G is a graph on n vertices and G is not a complete graph. Then vertex connectivity should be strictly less than by n minus 1. So why do you think it is true?
Because of that, man, theorem inequality degree is always less than n minus 1 if it is not complete graph.
Okay. So what is he saying? That we have this inequality that vertex connectivity is less than equal to edge connectivity, which is less than equal to minimum degree. Now you are saying that, so now if G is not complete, that means minimum degree is strictly less than n minus 1. Because if minimum degree is equal to n minus 1, that means all the vertices are connected with each other and we have a complete graph. But if a graph is not complete, then we have at least one, we have at least there are two vertices uv such that uv is not an edge, because it is not a complete graph, and therefore the minimum degree has to be strictly less than n minus 1. And using this inequality, then we get that this is strictly less than n minus 1. So is this question clear to everyone? So in general, so basically we have, in general, if G is a connected graph on n vertices, we have that vertex connectivity is less than equal to n minus 1. So now this theorem is saying that the highest vertex connectivity, which is n minus 1, can only be attained by complete graphs. Any graph which is not complete has to have vertex connectivity which is strictly less than n minus 1. Okay, is this clear to everyone?
Yes.
Okay. Now these are just implications of definition. So you just have to understand the definition and then tell if it is true or not. First is that if G is K connected, then vertex connectivity is equal to K. True or false? So what do you think? If G is K connected, then can we say that vertex connectivity is K? True or false?
It should be k minus 1. It is false.
No. So why it should be K minus 1? Why it should be K minus 1?
Because k connected means we have to remove k vertices, na ma'am?
No. K connected means that if we are removing K minus 1, if we remove any if we remove any K minus 1 vertices, then graph is remaining connected. And connectivity is the largest K for which G is K connected. So basically, if G is K connected, then is vertex connectivity K? True or false? If G is K connected, then it need not then K Kg can is not K minus 1. Vertex connectivity is the largest K for which G is K connected. So what about 1? Is it true or false? So this just follows from definition.
It is true. It is true, ma'am.
Why is it true? So suppose, see, we already did this thing. So if this was K4, this was K4. So is K4 1 connected? Yes. K4 was 1 connected. K4 was also 2 connected. But what was vertex connectivity? What was vertex connectivity for this? It was 3, right?
3.
So we see that K4 is 1 connected, but vertex connectivity is 3. Therefore, this statement is false because vertex connectivity is the largest K. So basically, if G is K connected, then we can, at most we can say that Kg vertex connectivity will be greater than equal to K, because vertex connectivity is the largest K for which G is K connected. And since it is K connected, then vertex connectivity has to be greater than equal to K. It need not be equal to K. We can look at this example only. For Kn, we know Kn is K connected for K equal to 1 till n minus 1. But vertex connectivity is n minus 1. So first statement is false. So everyone understand why first statement is false?
Yes.
What about the second statement? Second statement is saying that if vertex connectivity is K, then G is K connected. True or false?
This is true, ma'am.
Why? Why it is true?
Because this kg is
Hmm.
greater than equal to k, na? So
Yes, because Kg is the largest K. It is the largest K for which G is K connected. So that means Kg is, if if so what by definition what do we mean that if Kg is equal to K, vertex connectivity is equal to K, this means that G is G is 1 connected, G is 2 connected, and G is K connected. So basically G is M connected for all M less than K. In particular, G is also K connected. Therefore, second statement is true. So what I am saying is, this is the thing. If G is K connected, then this implies that vertex connectivity has to be greater than equal to K. And if vertex connectivity is K, that means it is the largest K is the largest number for which G is K connected. So that means G is M connected for all M less than equal to K. Therefore, so this just follows from the definition. So we see that second statement is true. What about third statement? If vertex connectivity is greater than equal to K, then G is K connected. True or false? What about the last statement? Is it true or false? So in particular I am asking, so what do you think, is it true or false? So we have just seen that if G is K connected, then that means vertex connectivity is greater than equal to K. Why? Because it is the largest number for which G is K connected. And if vertex connectivity was K, if vertex connectivity is K, that means G is K connected. G is K minus 1 connected. G is K minus 2 connected. That is, G is connected for all numbers less than equal to K. Now we are saying that vertex connectivity is strictly larger than K. Then will this imply that G is K connected?
True, ma'am. True.
True. Because if vertex connectivity is greater than equal to K, that means vertex connectivity is some K plus M, where M is a positive number. So that means G is K plus M connected. And if G is K plus M connected, it is also K connected. Therefore, this last statement is also true. So any confusion in any of these statements?
Ma'am,
Yes.
example one.
For one, why one is false, you are saying?
Yes, ma'am.
So
Once
see,
again, explain,
yes,
ma'am.
yes. So if I take my G to be K4, if I am taking my G to be, oops, what is this happening? K4, this is V1, V2, V3, V4. If G is K4, then I can say that K4 is 2 connected, right? So,
Yes, ma'am.
so in particular, I am taking K equal to 2. But is vertex connectivity of K4 2? Is it 2?
No, ma'am. Three.
No, it is 3.
Three.
So therefore this is not true, right? This is saying that if G is K connected, then vertex connectivity should be K. But in our case, if we are taking G is equal to K4, we know that it is 2 connected. But vertex connectivity is coming out to be not equal to 2, which is vertex connectivity is 3. So this statement is not true. So if a graph is K connected, at most what we can say is that the vertex connectivity will be greater than equal to K. That is always true, but it need not be equal to K. Is this doubt clear now?
Yes, ma'am.
Okay. So please read all these three statements like for the last time and see if there is any confusion in any of these any of the false or trueness of any of these statements. If there's a doubt, please ask. Okay. Now, okay. So let's, okay, G, two connected. So now in particular we'll study about two connected graphs. So what do we mean by two connected graphs? Two connected graphs means that first of all they are connected, and two connected. K connected means that if we remove K minus 1 vertices, then the graph should remain connected. So by two connected we will mean that if we are removing one vertex, then graph should remain connected. It does not and if we it does not depend on the vertex. That is, if we remove any one vertex, then like for every vertex G is 2 connected means that G minus, that if we take any vertex, then this should be true. That is, G is 2 connected means G minus V is connected for all V in V. Now we in the class there were some equivalent conditions which were done. So So first, this is by definition only, that G is connected and G has no cut vertex. And other equivalent conditions are this, that for every UV belongs to V, that is if we have two, so these are all equivalent conditions. That means these are all equivalent definition of two connected graph. So first definition is saying that it should be connected and it should have no cut vertex. That no cut vertex, which means that V is not a vertex set, vertex cut for all V in G. So this is just by definition. Now second definition is saying that if we take any two vertices U and V, for every two vertices U and V, we should have disjoint paths, two UV disjoint paths. That is, we have a path P1, we have a path P2, and P1 and P2. P1 and P2 should not have a common vertex. Thirdly is that any two vertices should be lying on a cycle. That means if we take any two vertices, they should lie on a cycle. And the last condition is that minimum degree is greater than equal to 1. In other words, we should have no isolated vertex. And any two edges should lie on a common cycle. That is, if we have an edge E1 and if we have an edge E2, we should be able to find a cycle in G which contains both E1 and E2. So these four are equivalent definitions of two connected graph. And what is a two edge connected graph? That now by definition, what will we mean by two edge connected graph? So can anybody tell me the definition of two edge connected graph?
If you remove one edge, the remaining graph should be connected.
Yes. So basically G is connected and G minus E. If we remove any one edge, G minus E is also connected. So this is the definition of two edge connected graph. And so now also we have that KG is less than equal to K dash G. So using this, can we say anything about, like, what implies what? Do we have, so if we use this two edge connect, so what is the implication? Is that two edge connected graph will imply two connected graph or the other way round? Which condition is true?
Bottom one is true, ma'am. Two connected graph is two edge
Yes.
connected.
Using this inequality, we can say that two connected graph will imply two edge connectivity. Why? Well, so why, Anupam? So why are you saying that this is true?
Because edge connectivity is having more weightage than, sorry, vertex connectivity has more weightage than edge connectivity.
Yes, yes, that is what it, but like if you want to give a proof using this inequality, how will you give it? So if G is two connected, then using my statement that I have, so what can we say about this? If G is two connected, what can we say? Is Kg equal to 2? Is Kg greater than equal to 2? Or is Kg less than equal to 2? Which of these three condition is true? If G is a two connected graph, which of these is true? So we in the, when we were discussing true false, we were, so if G is two edge connected, then what is true? What is the relation between connectivity and K connectedness? So we know that vertex connectivity is largest K for which G is K connected. So if G is 2 connected, what can we say? Vertex connectivity is equal. So what is true among these?
B is true, ma'am.
B is true. Yes. So if G is 2 connected, if G is 2 connected, we get that Kg is greater than equal to 2, because Kg vertex connectivity is the largest K for which this. Now so from this we get that Kg is greater than equal to 2. Now if Kg is greater than equal to 2, from this we get that K dash G is greater than equal to 2. Now if H connectivity is greater than equal to 2, can we say that G is 2 H connected? Will this imply if if H connectivity is greater than equal to 2, then will this imply that G is 2H connected?
Yes.
Yes. Why? Because if it is greater than equal to 2, that means it is some 2 plus m. So, which is saying that if we are removing less than 2 plus m edges, then this graph is remaining connected. In particular, if we are just removing, in particular, if we are removing just one edge, this graph will remain connected, and therefore, we see that two connected graphs are two edge connected graphs using this inequality. So, is this clear why this statement is true? This is true, and we'll see that this is false. We'll see. So for false, we'll still have to see. But is the true part clear to everyone? Is there any doubts in true trueness of the statement? Okay. Okay. So now we have some.
Ma'am, last.
Yes. Sorry.
Ma'am, last one.
As okay. Sorry. Yeah. Huh. Last one as in
Can you explain it again?
why two connected implies two edge connected?
Yes, ma'am.
Okay. So see. So if G is two connected, that means, so first, did you understand this, that kg should be greater than equal to 2 if G is 2 connected?
Yes, ma'am.
Now if kg is greater than equal to 2, now since we have that kg is less than equal to edge connectivity and kg is greater than equal to 2, so if we combine these two inequality, we get that edge connectivity is greater than equal to 2. Okay. So what is the definition of edge connectivity? It is the minimum size. So we are getting that minimum size, that is smallest vertex, smallest edge set, or let's say that. So we are saying that this will implies that if edge connectivity is greater than equal to 2, then smallest edge cut has cardinality greater than equal to 2. So in particular, we do not have edge cut of one edge, right? Is this point clear? That if edge connectivity
Yes,
is
yes,
greater than, then smallest edge cut has cardinality greater than equal to 2. In particular, we do not have edge cut of one edge, therefore G has to be two edge connected, because one edge is not sufficient, to make this graph disconnected. Is it clear now?
yes, yes, ma'am.
Is it clear? Okay.
Yes, ma'am. Yeah.
Okay. uh, okay, so now if this is clear, let's look at it. So this first statement is this: G is 2 connected if and only if G is connected and every edge lies. Okay, okay, sorry. Before this, we have this question. So first we have to show that G is 2 edge connected if and only if every edge lies on a cycle. So let's try to prove this. So if I'm saying, so basically we have that G is 2 edge connected. Then we have to show that every edge lies on a cycle. Now why do you think it is true? So basically we have to show this. Now suppose E is an edge in G. Now we have to show that we have a cycle in G. To show we have a cycle in G containing E. So why do you think it is true? So suppose E is an edge UV in G, and we are given that G is 2 edge connected. So what can we say? If G is 2 edge connected, what can we say about G minus E? If G is 2 connected, what can we say about G minus E? Is it connected or disconnected? Can we say anything about connected or disconnectedness of G minus E? We are given that G is a 2 edge connected graph.
It is connected, ma'am.
Yes, because what is the definition of 2 edge connectedness? That if we
To remove at least two edges.
yes, 2 edge connectedness means G is 2 edge connected means that if we are removing one edge, then graph is remaining connected.
Connected.
So we have that G minus E is connected. So now if G minus E is connected, so what can we say about U? What can we say that if G minus E is connected, that there is a path P in G minus E connecting U and V? Can we say this?
Yes.
Because G minus E is connected, so there's a path connecting U and V. So now do we, using this, can we, so suppose this path is P. So now can we say that G has a cycle containing E? So can you see any cycle in G which contains E? So E is an edge in G, and there is this path between U and V in G minus E, which we are calling as P. So now can we see there is a cycle in G?
Yes.
So if we look at this only, right? If we, E is an L, so basically, so if we look at G, UV is already an edge here because we picked it from G, and there's a path between U and V in G minus E. So this path is in G also. So we see that EP is a cycle. So one condition is true, that if G is 2 edge connected, then there is a then any edge is contained in a cycle. So is the first condition clear to everyone?
Yes.
Now what about the converse? Converse says that suppose every edge is contained in a cycle. then G is, suppose every edge is contained in a cycle, then G is 2 edge connected. So basically we are given this, and we have to show G is 2 edge connected. So if we have to show that G is 2 edge connected, what we have to show? First of all, what do we need to check? If we want to say that G is a 2 edge connected graph, what we have to check?
That there is a cycle, man.
No, no. See, we have,
Ma'am, removal of one edge, the graph is connected.
yes, yes, you're right. So basically, we are given that every edge is contained in a cycle, and if we have to show G is 2 edge connected, what is the definition of 2 edge connectedness? That means that if we if we remove one edge, then if we remove any one edge, the graph should remain connected. So suppose E is an edge in G. E is an edge in G. Now E is an edge which is UV. Now we are given that this edge is contained in some cycle. So we have to show that G minus E is connected. So can we say G minus E is connected?
Yes,
Why?
because if we remove E, still that is connected because it is only one connected.
So yeah.
Madam, because
Yeah.
every edge contained in the cycle,
Yes.
so E is in the cycle.
Hmm.
So removal of E, the remaining path is it will be connecting the path U and V. It is connected.
Yes, yes, you are right. So basically, what he's saying, so since E is contained in a cycle, since E is contained in a cycle, that suppose E was UV, so this E is contained in a cycle, so G minus E will have a UV path. So if we are removing UV, we are basically disconnecting U and V. But there is another path between U and V. Therefore, removal of this edge won't affect the connectedness of the graph. Therefore, we see that the converse is also true. G will have a UV path. G minus V will have a UV path. Therefore, G minus E is connected. So basically, in this question is giving us a nice, necessary and sufficient condition. So in class we did this is in class we see that for two connectedness, there are these nice conditions that G should be connected. G has no cut vertex. Then there is this condition also that for every UV we should have two UV disjoint paths. Then thirdly, that every two vertices should lie on a cycle, and if we look at the fourth condition, any two edges lie on a common cycle. No isolated vertex, but any two edge lies on a common cycle. So we had nice equivalent definitions of two connected graphs. So this exercise is giving us a nice equivalent condition for two edge connected graphs also. That is, G is a two edge connected graph if and only if every edge lies on a cycle. So if you want to check if the graph is two edge connected, it is sufficient to check that every edge is lies on a cycle. So is this question 1 clear to everyone? Any doubts in any of the parts? Converse or the forward implication? Okay. Now the next thing is this. So if G is 2 connected, then for every UV path P, there is a disjoint UV path Q. True or false? So now we are just saying 2 connected. That is, when we are not mentioning anything, that means we are referring to vertex connectivity. So what do you think? Is it true or false? Any guesses? What is it, true or false? That if G is
True,
2,
true.
why? Why is it true? You're saying it is true. Why?
Ma'am, we have already discussed this. There is a one this joint path, uh, whi- which because it is in cycle. So if we remove one path, still we have connectivity.
So see, this was the statement for two connected graph. For every UV, we have two UV disjoint paths. That is, if we have two vertices UV, we can find two disjoint paths. But this statement is saying something else. This is saying that if G is 2 connected, then if I take any path UV, like now I am specifying a path, that given a path P, I can find a path Q which is disjoint. But my definition was saying that for UV, because for UV, we'll have that there is a path P1 and P2 which are disjoint. But this is saying that if I am given a path P, then also I can find the path which is disjoint from Q. So this statement is different from the statement which is mentioned. Right? So do you understand the difference between these statement
Yes.
definite?
Then, ma'am, it is false because we cannot fix that path.
Huh. So if you are saying it is false, then we have to give an example also. So can you give an example? Try to give an example. So you are right, this is false. This is false. So what kind of example do we have to give? We have to give a two connected graph, and we have to give a path P. Suppose, like, I'll give a graph, then you, so suppose I am taking K23. If I am taking K23, so we are saying that statement is false. So that means you give a path between, say, give a path P between A and B, such that there is no disjoint path, such that there does not exist Q, such that P intersection Q is empty. So if we are saying this statement is false, so I'm telling you it is false, and I'm also telling you this graph will give you a counter example, K23, and I'm also and also it will be an AB path. So you just have to give AE path. Give okay, no. What is the path basically in this? Okay, this example won't work, I think. Uh, Wait. Suppose I am removing AE now. Uh, okay.
Ma'am, we can draw
Then
two sets, and then we make a path so that if we remove one, you can make two
two. Yes.
circles,
Yes.
then connect like one V and one like that.
Okay. So we connect to. Okay. What you are saying is. So you are saying draw two circles. This, okay, yes, but this is it two connected? But this is not two connected, right? Okay, so maybe, okay, this statement is false, but okay, so I'll give a counter example in next session maybe, but I can't think of it, but it is false. So so we'll look at the counter example in next session, next thing. But so you can see why it should not be true, because our definition is saying that we are getting two disjoint path, but it is not saying that if we are given a path, so it does not follow from the definition, but we still have to give a counter example. So uh, so let's leave a counter example for now and move on to next. So we'll discuss this next time. Okay, so the next question is we have to find vertex connectivity and edge connectivity for this graph. So what do you think? Is this graph, so let's first find out the vertex connectivity. So what do you think? Is this graph one connected? Is G1 connected?
Yes.
Yes. Is it two connected?
Yes.
Okay, why it is two connected?
Ma'am, if we remove one vertex,
Hmm.
still it is connected.
Huh. So if we remove one vertex, it is still connected. Why? So so basically you have to, so you maybe use any of the equivalent definition. So you see that if you pick any 2 points in this graph, those 2 points will be contained in a cycle. Or if you or if you remove any one vertex, since we are this is two connected, and you can use one of the equivalent definitions, like you can see that any two vertices are contained in a cycle, therefore it is two connected. What about 3? Is G3 connected? Is G3 connected?
Yes.
Okay, why is it 3 connected? That means if you remove any two vertices, this graph should remain connected. That is, there is not a vertex set of two vertices.
Yes.
Vertex cutoff.
Yes. We can remove two, still it is connected, ma'am.
Did you check for every pair of vertices? Do you think if you I think it is not I think it is not 3 connected. That is, you can find a vertex cut of size 2.
Madam, the removal of B and E, the graph is disconnected. So it is not a three connected.
Okay, wait. So you are saying removal of B,
B and E, E.
this B and E.
Graph is disconnected.
So if you remove B, so if you are saying this, so what two vertices can't be connected? You think?
Ma'am?
Huh. So if it is disconnected, that means so okay. If you
The
are,
graph is not three connected.
yes. So basically, see, huh. So if we remove this, the result A, B, and E, the resultant graph is A, C, D. So we are, yeah, and so we can see that we are getting at least, we are getting two components. So basically, there is no path between. So if we remove B and E, then there is no path between A and I. Therefore, this graph is becoming, so if S is equal to BE, then this graph is becoming disconnected. Therefore, this is not 3 connected. So now, what is the vertex connectivity then? What is the vertex connectivity of this graph?
2, ma'am.
2. Good. What about the edge connectivity? So
One,
can
one, ma'am. One. So no. One.
is G, so we see that G1
Two.
is G is one edge connected. Yes, because G is one edge connected because there is no bridge like edge, that if we remove, sorry, G is one edge connected, that because it is connected. Why is G two edge connected? So we have done an equivalent condition that G is two edge connected if every edge is contained in some cycle. So you see that if you pick any edge, it is contained in some cycle. Therefore, this G is also two edge connected. So is everyone clear why G is two edge connected? Because
Yes.
if we'll remove one edge, then the connectivity of graph won't be affected. Every edge you can see is contained in some cycle. Therefore, this G is also two edge connected. What about 3? Is G three edge connected? So in this question also, first you can see that you cannot use this inequality directly. We were trying to, that kg is less than equal to k dash g is less than equal to del g. So in this graph, this is coming out to be 2. And what is the minimum degree? Okay, minimum degree is also 2. So you can say that edge connectivity is 2 using that also. Because, right, what is the minimum degree of this graph? 2.
Two. Two.
Because if we look at this, so and using this inequality, we can conclude that vertex connectivity is 2. Oh, sorry, vertex connectivity and edge connectivity is 2. Now, edge connectivity is 2. That means there is an edge cut of size 2. So can you give me an edge cut of size 2? That is, removing those two edge will make this graph disconnected.
IJ and CE.
Yes. So we can see that CE and IJ is an edge cut. Because if we remove these two edges, then this graph has two components and this is becoming disconnected. So in this case also we see that all these three things are coming out to be 2. So now we have this graph. So now we have this graph. So first of all, what is the minimum degree of this graph? What is the minimum degree of this graph?
3, ma'am. 3.
3.
3.
Okay. Now let's look at the vertex connectivity. What is the vertex connectivity? So is this is a connected graph? So it is 1 connected. What about 2? Is it 2 connected?
No.
No,
No,
ma'am.
ma'am.
Why?
Because if we remove E, ma'am, then it is disjoint.
If we remove E, then it is becoming disconnected.
Disjoint.
Disconnected. Therefore, it is not 2 connected. So what is the vertex connectivity? Vertex
1.
connectivity is 1. Now you see, if we apply that inequality, we cannot directly conclude about the edge connectivity, because this is coming out to be 1, this is coming out to be 3. So now this just say that edge connectivity is 1, 2 or 3. So using this inequality we cannot conclude. So we'll have to check it manually. So first of all, is this graph one edge connected? So it is connected. So if we remove, so it is one edge connected, because if we remove 0 edges, this is. What about 2? Is G2 edge connected? Is G2 edge connected? That means So what do you think? Is it two edge connected? Is this graph?
Yes.
Why?
Yes, ma'am.
Why?
By removing one edge,
Hmm.
the graph also connected.
Yes. So can you give a reason? Maybe one of the using one of the exercises that we did.
Cycle, ma'am, we said na, that
Yeah.
is if it is cycle.
Yes. So we see
Every
that every edge is contained in a cycle. Therefore, if you look at any edge, it is contained in a cycle. Therefore, it is two edge connected. So now, what about three? Is it three edge connected? Is it?
No, ma'am. No.
Why?
Because removal of two edges, the graph is disconnected.
Which two edges?
B, C and G, C.
E.
Sorry, B, B and G.
This one, right?
Yes, right, ma'am.
Yes. So see, if we remove these two edges, that means it is becoming disconnected. Therefore, we see that these inequalities are not, like, these need not be equal to, because in this case we are getting strict inequality. That is, minimum degree is 3, edge connectivity is 2, and and vertex connectivity is 1. So all these three numbers can be distinct also. We can see this using this example. Okay. Okay. Yeah. So now in this only you can see that, so this is a, so we were stuck on that counter example. So in this only we can see that this is two edge. Okay, no, but it is not two connected, so we cannot. Okay, no, no, nothing, sorry, this is not a two connected graph. Oh, okay.
instead of E, ma'am, we have to take two paths. Then we can give the counter example. I will also give you next time.
Yes, okay. Huh, maybe, yes, you, like, okay, yes, the example will be possible. Okay, yes. Okay, so now, okay, so now lastly, okay, so lastly we'll discuss something on networks. So the last thing is on networks. So this was all about connectivity. Now we'll discuss, now we'll look at the networks. So first of all, what is a network? Network is a, so now we are looking at directed graphs. So by directed graphs we mean that every, so it is a graph in which every edge has a direction. So instead of just simple edges, we'll have a direction. So that is what is a directed graph. And also, what is a network? So there are three things. It is a directed graph. Secondly, each edge is assigned some number which we called capacity, and it has two distinguished vertex, source and sink. So you can see, this is an example of a, this is an example of a network. So for network we mean three things. First, it should be a directed graph. So in this graph you see that every edge has a direction. So now edge will be written as a uh, SB. So in this graph, SB and BS are not a same thing, because we are also assigning a direction. So this, so we, for a network we need three condition. A, it is a directed graph. Second, each edge has a capacity. So we see that every edge has some weight assigned to it, which is called as capacity. And third, it should have two special vertices, source and sink. Two special vertices, source and sink. Source vertex is basically a vertex S, such that we have all the edges going out of S. There is no edge coming into S. That's why it is called a source vertex. And then we have a sink vertex. Sink vertex is kind of a opposite of source, that is all the edges are going into a sink. There is no vertex which is going out of it. So in this example, S is a source vertex because there are two edges with, it has only two edges which are going out of it. And similarly, T is a sink vertex because all the edges are going into it, but there is no edge which is going out of it. So if we have these three properties, that it is a directed graph, each edge has a weight which we called capacity, and that graph has two special vertices called source and sink, in this sense that source has all the vertices, all the edges are going out of it, and sink all the edges are going into it. If a graph has these three special things, then we call that graph a network. Now once we have a network, then our aim is to, given a network, our aim is to find the maximum flow. So what do we mean by flow? Flow is a function. Flow is a function from basically edges to R. Set of edges to R. Set of edges to R such that it is satisfying these three properties. First, that this flow should be less than equal to the capacity. So if we take any two vertices, any two, so if we take any two edges, if we take UV is an edge, then that UV is an edge, then U has some, this UV edge has some capacity to it. So the flow that we are assigning to it should be less than equal to the capacity. That is, flow should not exceed the capacity. Second, we have the skew symmetry, which we rarely need, that FUV should be equal to minus FU. Third is an important property, which is the conservation law. That is, if we pick any vertex which is not equal to source or sink, then the flow V is a vertex which is not a source vertex, neither a sink vertex, then the flow coming into V should be equal to the flow going out of V. That is, coming into V, we look at all the edges which are coming into V, and we add the flow to it, and similarly this. So this is the conservation law. So let's understand this with an example. So the black numbers are the capacity, and claim is that purple numbers is the flow. So if to check it is a flow, three things should be satisfied. First thing is that the flow should be less than equal to the capacity. So in this example, you see that 1 is less than equal to 2, 1 is less than equal to 2, 0 is less than equal to 1, 1 is less than equal to 3, 1 is less than equal to 1, 1 is less than. So this first property is satisfied. Second is skew symmetry. So there are no edge, two edges like UV and minus VU. So skew symmetry is trivial. And third is the conservation law. So conservation law, what do we have to check? That if we take any vertex other than, so that for every vertex which is not a source vertex, neither a sink vertex, then the flow coming into that vertex should be equal to flow going out of that vertex. So what are the vertices other than sink and source? They are A, B and C. So we have to check the conservation law for A, B and C. So is conservation law for A satisfied? What do you think? So basically you have to check that flow coming into A should be equal to flow going out of A. So is
Yes.
it satisfied?
Yes.
Why?
One is, ma'am, coming and one is going to A.
One is, so coming is 1 plus 0, which is 1, and going is 1 also. So flow is, so this is done. What about B? Is it true for B also?
Yes.
Because coming is basically 1 and going is this 1 plus 0, which is 1. So we see conservation law is satisfied for 1 also, B also. What about C? Is it satisfied for C also?
Yes.
So it is also satisfied for C. So So does everyone understand the definition of flow? Okay. So if you understand the definition of flow, now, so this is the question. So in this question, you are given a graph, and this has flow. Okay. So there's one more definition. What is the total flow? To, if we are given a directed network with flow, then total flow is basically, it is equal to flow coming into sink vertex, and which is equal to flow going out of sink vertex. So first question is asking, so this question is asking, we have to give appropriate directions to each edge so that conservation law is satisfied. So now total flow is 2. That means the vertex, source vertex, the flow coming, and this number is giving us the flow value. So the numbers which are written are giving us the flow value. So we have, now total flow is 2. That means the flow going out of source vertex is 2. So we see that S is a source vertex, T is a source vertex. Now for each edge we have to give a direction. So what should be the direction of SA? Is it, should it be SA or AS?
SA, ma'am.
SA, because S is a source vertex. What about SC?
SC.
Okay. Now, what about now? And similarly, T is the sink vertex. So BT will have this direction, and DT will have this direction. Now, what about the direction of AB?
A to B.
A to B. Why?
Because zero flow is there on the both, and so only one flow is which is coming is going to the B.
Yes. So basically, since there is a flow of 1 coming into A, so number 1 should also go out of A. And there are just 2 more edges. So since this is 0, this won't contribute to anything. So AB should have this direction. And what about CD?
Same, ma'am. C to D.
C equal to D, because there is flow of 1 coming into C. And what about AC then?
No direction.
It can have any direction basically, since you can, like, it won't affect it, so you can give any direction to the flow which are 0. So we see that if we give these particular direction, then the conservation law is satisfied. So this was, so okay, so in this was it. So this, so now then there is this algorithm to find the maximum flow, which will be done in the next week. So now, do you have any doubts from, this was the last question, do you have any doubts from the connectivity or the definition of flow and the directed graph? If you have doubts, you can ask. So our today's problem fine?
Yes, ma'am.
Okay. Okay, then I'll end the session.
Ma'am, one request and suggestion, ma'am.